Shall I start?
Yes, please.
Okay. Good afternoon, everyone. My name is Shuhao, and I'm a research fellow for Optical Bioimaging Lab in the US. Today is a great honor here for me to be invited by NOBIC and give you a micro talk so as to advise on our recently developed microscope technique called LSFMM, which we believe is a good image platform for high-speed 3D confocal imaging. So before I will introduce some background. So our technique is based on the fluorescence microscopy, which is the most commonly used in biological studies because of its high resolution and high specification. The diffraction limit resolution will make it able to visualize microstructures down to cellular or subcellular level. The use of the fluorescent properties to analyze the composition can help to observe the specific components we want. We can analyze multiple components in multiple colors using different wavelengths, excitations. So we can also use it as to acquire volumetric image and time-lapse image. And also its image scale can range from one single cell to also very high float by shifting its objective lens with different combination. There are many commercialized microscopes available in the market. I believe many of you have used some of these type of microscope from those big manufacturers, such as Olympus, Nikon, and Zeiss. For most routine experiments, the first one, the inverted and upright wide field fluorescence microscope can meet most requirements. But sometimes if we want to do 3D image with some optical sectioning, a laser scan confocal microscope will be a good choice in the market. However, its image speed is usually limited by the point scan mechanism. It cannot observe very fast biological dynamics. And there are also another type of super resolution microscope usually available in the microscope facilities, such as the Unstorm from Nikon. They're usually used to obtain fluorescence structural image with super resolutions. But the cost is that the speed will be very slow and it required special fluorescent labeling. So nowadays, among the biological research community, there's a growing need for fluorescence imaging. They're expected to fulfill all these four requirements, which are clear, deep, fast, and live. And in space domain, the image modality should be able to image at very high resolution. Usually should be able to resolve down to subcellular level. Also, the second space domain requirement is to image deep, which means to be the penetration depth to be large enough to cover the large ROI, region of interest in the animal organs, such as the mouse brain. And in time domain, the temporal resolution should be very high to resolve any of the fast dynamic biological process, such as the blood flow. And besides, the image process should remain very stable so that the live tissue or live animals can be used to do the time-lapse observations. But until today, there still not exists a very good solution that can achieve all these imaging requirements at the same time in one single microscope unit. The most challenging one actually is the deep tissue imaging. The reason why, because it is so difficult to achieve, because then right is what is very valuable for us to achieve it, because we want to resolve the microstructure details in the deep regions. Sometimes neural structures and connections usually happens in the thick brain area. So people now they want to image very deep in the mouse brain or some animal brain. So we want to create a 3D model for developing organs and tissue with high resolutions, with a non-invasive way to using the fluorescence microscope. The biggest challenge for deep tissue imaging is the scattering light in the tissues. There's an unwanted light come from the out of focus plane or even the tissue itself and generates a scattered photons. This is an unwanted background and which will degrade the image quality and we image deep. And also the light will also attenuate when we get deeper into tissues and the background will finally dominate the signal. So to address the issues and also maintain the image speed, there are many solutions available in research community. One of them is the light scan confocal microscope. This is adapted from the traditional point scan confocal microscope. The implementation is very simple. Instead of scan the sample point by point, scan line by line by using a cylindrical lens, and thus largely decrease the frame rate. And similarly, the optical sectioning can be achieved using confocal slit instead of a pinhole. So in this way, although it sacrifices some sectionability, but the performance is still better than a wide field microscope. The second solution is the spinning disk confocal microscope. We also borrowed the idea of a parallel scan on top of the confocal microscope. We use a rapidly spinning disk featured with patterns of holes to scan multiple lines, focal points across the specimen. Thus, the confocal image of the whole region of interest on the specimen can be rapidly captured by cameras simultaneously. However, the optical section also no better than the normal confocal microscope because there's a phenomenon called the pinhole crosstalk, which means that some of the fluorescent emission from outer focal plane can return through the wrong pinhole and contributes to the image background and noise. Then the light sheet microscope is another solution. Use a very thin sheet of light to illuminate the specimen from the side and collect the fluorescent emissions in the orthogonal directions by the CCD camera. So in this way, the photo bleaching effect is very small. Also, because you use the wide field detections, so the image speed is very fast. Nowadays, the light sheet microscope is regarded the gold standard for three-dimensional image for relatively transparent small animals, such as the zebrafish, fruit fly. However, when it comes to image thick and non-transparent specimens, the image resolution will be very poor because of the light scattering in the tissues. And also another big issue for light sheet microscope is that the mounting of the sample is very tricky. It's very difficult to mount it in a very tiny space, especially in this chamber. So the optical alignments of the objective lens should be special designed. And when we talk about the deep tissue imaging, the multiphoton microscope is currently the gold standard because it uses a nonlinear excitation of focus, and only a small volume can generate fluorescence at the focal point. And then people have used the technique called multifocal excitation so that it can largely increase the frame rate. But the same issue happened with the spinning disk confocal microscope is that it can cause the crosstalk. And similarly, its signal to background ratio is not better than the traditional multiphoton microscope. And also the cost of this type of multiphoton microscope is very high. So the system is very complicated, bulky. It's not very suitable for universal research. So then we come to our solution, focal modulation microscope, which is proposed in our lab in the US, and it can achieve both cellular resolution and high penetration depth at the same time. The first generation of focal modulation microscope is a point scale version, and its experimental layout is showed here. We developed 3 generations of FMM system. Then the first system is based on the actual mirrors, but the speed is very slow. The modulation frequency can only be a few hertz. Then the second generation, we designed used a coastal optical modulator. The modulation frequency can go up to 10 megahertz, but it suffers from the low modulation depths and cannot generate complicated phase patterns. So in the third system, we use electro-optic modulator and, combined with spatial polarizers. It can also modulate at 10 megahertz, then generate maybe patterns combinations. So we can have the modulation that focus more flexible. However, all this setup is based on point scan. So the first generation in 2016, we combined it with the line scan technique. That's why we call it the LSFMM, which means the line scan focal modulation microscope. The feature of this system is it has a very high image speed, can image more than 100 frames per second, can capture 3D and 4D images with live transparent animals, such as the zebrafish. You can see the image comparison of this LSFMM here. And here I made the summary of all the solution mentioned previously. We can see that the LSFMM has an outstanding performance in terms of the image depth, resolution, and speed. Also, the system simplicity and cost is very reasonable. And the other solutions more or less have 1 or 2 shortcomings. Even so, the current LSFMM is lab scale, and we believe it will be a good image platform. So now we can take a look at more details on these lab-based LSFMM systems. In this system, we are using the electro-optical modulator and a spatial polarizer to achieve the fast phased modulation. Then this modulation finally generates the intensity modulation at the focal plane, as you can see from this figure here. There are only intensity excitation modulation at the focal plane. In the outer focal plane, there are no modulations. So in this way, when we do the demodulations, we'll only collect the emission signal from the focal plane. Then we remove the outer focal backgrounds. In this way, we can enhance the penetration depth in the thick tissues. And in this system, we use the SCMOS camera to capture the image. As you know, the SCMOS camera has a very high speed. So we can use it to capture image in video frame rate. This system is 100 frames per second. And here are some image applications. The first case is on the image of the single polar grain. And we scan the 3D volume, as you can see here. The line scan FMC at red can provide better optical sectioning than the conventional confocal microscopes. You can see the spines only at the focal plane. So in this way, when we do the reconstructions in Z, using all these Z slides, we can get a very good 3D rendering results of a single polar grain. And the second case for our application is on the 3D pathological study on the excised tissues. You all know the conventional HE stain image protocol is very labor intensive and time consuming. And it needs to prepare very thin slides, less than 5 microns. Now we can use the LSFMM system to do the whole tissue's image. The procedure is very simple and fast. We only need to do is the staining, clearing, and then we scan the tissue volume under the microscope. And here are the image results of the chicken catalytic tissues stained with dye called LC. The LSFMM system can image very clear section image. So you can see, compare with a conventional confocal microscope. Then we do the rendering. Then we can reconstruct the 3D tissue volume as presented here. You can see this is a 200 microns thickness chicken catalytic tissues. The third case is the calcium image of the small animal, zebrafish. We use calcium indicators. Then we apply some morphological mirrors image using the LSFMM. Can remove the most of the out of focus background with a very clear image. Then we use it to check the calcium neural signals of the spontaneous activities. You can see that compared with the confocal microscope image, the LSFMM have less background and better sectioning ability. Can capture only the focal regions with signal fluctuations. So we can get a larger dynamic range of intensity after post-analysis, which is good for quantitatively analysis. And since we already validated the performance of LSFMM in lab scale, we want to move forward to push it from bench to the commercialized product. So we want to reduce all these optics to a modular prototyping microscope, as you can see here. Generally, our design is consists of a laser unit, scan optics in the center, then the microscope frame used as a stage to hold the sample. So to do this thing, we formed a startup company in 2019, which is based in Singapore, called Focal Precision Instrument Company. And this company is an exclusive patent license on our patent called focal modulation microscopy system and methods. So based on this company, we decided to design our scan box, which is our core product. We designed the scan box as I showed here. And the configuration, we have at least three configurations: the standard one, the advanced one, and premier one. But this is for standard one. We only have one single lasers and use the CMOS camera. It's a very basic frame for very basic research. And for advanced one, we have provide two lasers, and then we combine with some like a motorized stage, use the microscopes. And the premier one, we have included all the most advanced functions of the techniques, like the four colors of laser engine and the scientific CMOS camera to achieve the most highest frame rate. And microscope we use is the most advanced one from the Olympus. And here's the parameters for the our product configurations. The highest frame rate we can achieve for the system is 210 frames per second to observe the fast cell dynamics. And we can image very deep in cells and tissues, which is at least 2 to 4 times deeper than the conventional confocal microscope. And because we use a CMOS sensor, we can capture a very large field of view. And the noise level and the dynamic range are also very good because of our camera. So we provide 4 colors wavelengths. Can also combine the super resolution features by using the technique called array scan. And this is the software we designed using our techniques. And here shows the image software panel for real-time acquisition. The user can use this to adjust the exposure time and acquire the Z volume, then do some post-processing, use this software. And this is the actual product we made. Actually, we have already delivered 2 sets to our customer in Shanghai University. And this is the real image. And we also have our place in the US here. And the customer can also customize their product based on our LSFMM scan unit. Firstly, they choose which level of scan unit they want. Then we can select the laser combination for them, up to 6 lasers they can choose. From the violet lasers to the infrared lasers. And our scan unit can be adaptable to most of the commercialized microscope frames, such as Olympus, Nikon, Zeiss, and Leica. This inverting microscope model can be directly adapted to our scan unit. Currently, we only have designed the scan box for inverting microscope, but later we will come up with a solution for the upright microscope. And can also provide additional accessories such as motorized XYZ stage and stage top incubators if we want to do the live cells image. And auto focusing module and spectrometers if we want to do spectral imaging, and TCFPC if we want to do the time-related imaging. And in the last slides, we'd like to acknowledge to the Optical Bioimaging lab because all the research work was done in this lab and supervised by Professor Chen Guan. And also acknowledge from the support company Focal Precision Instrument because it can give us support to push forward to this product to the market. And the CEO is Mr. Zhou Li. And currently, the company have achieved a revenue of about 1 million Singapore dollars until last year. So we believe the development of this company should be good. And also want to acknowledge the Collaborator. Currently, we already have local suppliers from the Singapore, and also we have some good suppliers can support us very good quality of laser, camera, optical components, and microscope, especially not in China, but also somewhere in South Asia. And the local collaborators, we have Syntron to push forward to the market, and some fabrication collaborators to help us to build a prototype scan box. And that's all. Thank you.
Thank you, Shuhao. So now, if any one of you have questions to the talk, ask. Yes, Claudia.
Hi, Sean. Very interesting. It's a really cool, startup idea that you're working on. I was wondering when you were showing some of the, various images and 3D reconstructions, you mentioned that it went through sort of processing and, sort of remodeling and that sort of thing. I guess I was wondering what program you've used for that. Is that compatible, for example, with Amaris or other image processing software, or is that a specific software that you've developed for your scope?
You mean that this 3D volumetric image?
Yeah, exactly.
Yeah, this 3D image rendering is achieved used software called Amaris.
Yeah.
Which is a commercialized software. But we already developed our own 3D rendering processing software by ourselves, which is based on some open source software. As you can see, we have present this processing software. This one is based on open source software called VA3D. Its interface is not good as compared with the commercialized one called Amaris, but we are now adapted to adjust our own software, want to combine, integrate into our own acquisition software.
I see. So in general, the images that you'll be generating are compatible sort of to be used with Amaris or with ImageJ, that sort of thing. Yeah. Okay, thank you.
I'm Harris. Thank you very much for your presentation. I have a question regarding tissue processing, because you showed neurons where you did calcium imaging, and then you also showed the chicken cartilage. As far as I understand, for calcium imaging, the tissue was live, of course, but then for the chicken cartilage, you did tissue clearing, right?
Yeah.
Yeah. So then when we use a live tissue sample, how deep can you go?
Yeah, it's a very good question. Usually, if a live tissue samples is very, we don't know if we do after we do the clearing, the tissue is still alive. So sometimes we prefer to not do the clear first. Then if the tissue is not that thick, we can still obtain the 3D image of this tissue volume. But if we want to image very deep of this tissue, like such as 1 millimeters in thickness, we may want to do the clearing, because all the single photon excitation microscope cannot achieve that deep without doing the clearing. So it is a very good direction to investigate whether the clearing will cause any.
I mean, the clearing, the clearing definitely will not. I mean, I think it will kill the cells. So if, let's say, we bring a live sample, just fresh tissue, like what is the depth of imaging that we can achieve? Will it be like 40 micrometers, for example, 50, based on your experience?
Yeah, this will depends on the scattering coefficient of these tissues. Let's say if it is a skin tissue, the scattering will be very high, so the image depth may not be very large, maybe 200 microns within 100 to 200 microns. But if the tissue is not that scattering, maybe using our technique can go up to 500, 600 microns in thickness. Because of this, actually, to be honest, this chicken cartilage tissues, this one we didn't do the clearing. We also can image up to 200 microns in thickness.
Right. And then I see here that you used a 20x lens. Can you go up to like 63 times, for example? Is that feasible with this microscope?
You mean the
magnification?
high
Yes.
magnification objective lens? Yeah, it should be available, but the thing is that when you use a high magnification lens, the working distance is also reduced. So if you want to image deep, usually the 63x lens is the working distance is only 100, 200 microns.
Okay. I'm asking because a lot of us are working with bacteria.
Yeah.
So 20 times, for example, might be like not enough for most of us to be able to image bacteria in a tissue. That's why. So I think in our case, we would definitely need something like 40 times or 63 times.
Yeah, 40 times should be fine for large working distance.
I see. Okay, that's all. Thank you very much.
Thanks for your question.
We have one question in the chat. The question is, amazing product you have there, Shuhao. I was wondering what is you would recommend using LSFM for my skin? Okay, this was already, yes, this probably was already answered partially by Harriet's questions. Okay, any other questions?
I just had one other question. In terms of, I know with some other microscopes, for example, say a lattice light sheet, depending on the different sample that you're using, there can be a really large amount of troubleshooting and optimization to get it to actually do what you want. I guess in terms of, like you mentioned, that different tissues, different samples have different levels of scattering, and that can, really affect what you can do with it. What is your sense for if you were coming to your scope with a completely new sample? Is it likely that there would be sort of quite a large period where you're needing to do that troubleshooting and optimization stages before being able to get clear images?
Yeah, there's many samples for applications. So usually the most frequently used is a zebrafish. So that's why the light sheet microscope is really popular, because zebrafish is a relatively transparent animals. But when it comes to other type of animals, a tissue like the mouse brain, if you want to do the live image, it will be relatively difficult. You must have a device to hold the mouse in live state data. So this setup, you need to do your own customization to hold the mouse under the microscope objective lens, and this should be another things to design. The other tissues like the live tissues, which is only cut from the exercise tissues. This one don't know how it works in a hospital or pathologist. But for our case, we only cut it into a very uniform shape. Then we mount it on the glass slide, and then this can be used for microscopic image. Yeah. So that's what I understand from these three types of tissues and samples.
Thank you.
If there are no more questions for our speaker, yeah, thank you, and us recording.